So what I wanted to really talk about today is the concept of math hacking. And it's kind of, math hacking is something where you can pre-process the data in a certain way or kind of look at generating functions to improve neural networks or improve AI methods in general, or potentially bypass them altogether by using some interesting little hacks that you find in how functions are generated and distributions are created and all that. So let's go ahead and get started here. So the talk is math hacking. So just a little bit about me. I'm the principal data scientist at Data 317. It's a consulting company. I've been doing this for a few years now. I've worked in a bunch of industries, government, healthcare, marketing, you name it. I've pretty much touched it. Worked with a bunch of fantastic organizations like the Man Jump, Springbuck, KSMC, and the state of Indiana. And the big thing, as you can probably tell from this talk, I love finding hacks that solve big problems. It's like a heist. And it's the highlight of this work. So let's continue on here. So, kind of cribbing off of the previous talk a little bit, some problems I see a lot in data science, artificial intelligence, and machine learning, they kind of span the gamut. A lot of times, a lot of the algorithms really don't scale. They are really slow. They take really expensive hardware to run. They don't grow very well with the data that you have, just because you have to start adding new neurons on, you have to start adding new layers, you have to get really funky with your architecture. Another problem, and this goes with the Xena Python that we all are probably very familiar with, is that they're really complicated. What I mean by that is that it takes a lot to get even just a simple answer out. A lot of architecture, a lot of everything. I saw in the Slack that we were doing addition with a neural network before. And yeah, there are some problems that you get from neural networks just by how they work, where the operations don't correspond directly to an answer right away without adding more and more and more layers. And the biggest problem that you run into with a lot of AI algorithms in general is that it rarely answers the question why. These algorithms frequently are black boxes. Things get weighted a certain way just because the algorithm sees that's how it gets to its minimum error. And, you don't actually know what it's waiting for. It could be doing things like it's selecting certain features that the programmer who's made this algorithm finds abhorrent, but it just kind of works out in the math that seems to be an indicator because of other reasons that are outside of the data set that you have. And just to kind of further this point, knowing why is central to anything that you do in data science. You have to know what the generating function is. You have to try and remove as much bias as you can. And you have to be able to express things in a clear and concise way. So when the algorithm that you're using or whatever technology that you're using breaks, and it will, because it always breaks in certain circumstances that you didn't plan for, that you can explain why and you can fix it. So knowing why is central to being successful in data science, artificial intelligence, machine learning, and really delivering value for whoever you're building these algorithms for. So let's talk about math hacking, what this talk is really about. So you've probably heard the term feature engineering before, where you're combining certain fields, you're separating certain fields, you're calculating certain fields. Math hacking is kind of feature engineering on steroids. It focuses on the mathematical aspects of problems that you're solving. So you're dealing with like distribution functions, you're dealing with vectorization, you're thinking a lot about, what is the essence of the problem that you're trying to solve, and what do these functions actually mean if you're looking at things like a number line and you're applying a polynomial on it, x squared or something like that. What is that actually doing to that number line and stretching it out and all that? And what do you know from calculus that actually tells you about the flow of that function and what it's going to do down the line and how you compute those gradients if you're training a neural network or something along those lines? Frequently, you'll see that math hacking serves as pre-processing to other algorithms, which is great, and it's fine. But it often serves as the solution as well. In fact, the examples that we're going to focus on is where the hacks that we discovered just by looking at the math and looking at these distributions and the generating functions were the solution that, allowed us to skip past the neural networks, allowed us to skip past random forest, allowed us to skip past all this other stuff and just get to the answer in a very scalable way, which is necessary in any kind of cloud solution that you're going to provide. And the beautiful thing about it too is that it bypasses a lot of complication. In general, math hacks, if you really understand generating processes, the functions that drive these results and that sort of thing, you can bypass all the architecture that you have to be worried about, all the concerns about vanishing gradients or other things like that exist within the math of a lot of these networks. And you can explain why you came to an answer that you actually have. So, I mean, in short, math hacking is really just being a total math nerd and seeing if you can come up with the fundamental function of the process that you're trying to explain and understand and predict off of, rather than having a function approximation. And to be clear, it's not always the case that you can do this. It's a lot of times you can. A lot of times it's being very clever with how you solve problems, but sometimes the problem is just really super duper complex and you do need to apply some of the methods that have been previously talked about. So the best part of this is always showing examples. So I want to talk specifically about some hacks that I've worked on in the past and how we've bypassed a lot of the nonsense that you get sometimes when you're looking at applying like rules engines or things like that. Not particularly artificial intelligence or anything like that, but in general, the very complicated systems that we as people like to develop to solve some of these problems. So I was working with KSMC at the time with a team of data scientists, and we got called into the state of Indiana to look at tax returns and see if we could build a solution that detects fraud. At the time, they were manually reviewing all the tax documents, tax returns that they would get, and were flagged for a variety of rules that they would just run through some Oracle database. And these rules were often sanity checks, that sort of thing. Basically, did you request too much given the income that you had? Did you request too little? Did you pepper in a bunch of returns one after another in order to get more back? A lot of things like that. And one of the things that we had to deal with while we were there is that we had several competitors that were selling these extraordinarily expensive systems that claimed to use all these very complicated methods to detect tax fraud. And they might have worked. It's just that I was a little nervous about a black box solution for this problem. And so we decided to do the other thing. And in case you guys all couldn't guess, tax law is super complicated on its own. And that was something I did not want to have to memorize. So when we were approaching this problem and when we were looking at actually trying to solve it, we started asking questions about, like, what does it mean to be fraudulent? What does it mean to, try and make up numbers in order to get some return back? And what it ultimately came down to was that all fraud is someone creating a number out of thin air or to some rule that they've observed that they can take advantage of the system and not following the economy as a whole or the tax code as a whole. And so we started researching and we asked, can we detect that behavior? And it turns out that you can. And this is the math hack. It's something called Benfords Law. So if you all were to open your credit card statement, one of the neatest things that you can do using Python and all that stuff is that you can look at the first digits on the purchases that you make, the first digits of the amounts for the purchases that you make. And about 30% of the time, in general, I mean, there's exceptions, but 30% of the time, that number is going to start with a 1. 15% of the time, it's going to start with a 2. 7.5% of the time, it's going to start with a 3 and all the way down. It's a power law, and it's called Benfords Law. And it's really, really cool. It was discovered in the 1930s by a physicist who noticed as he was flipping through these things called log books, when you used to have to manually look up logarithms, that folks were always in the front of the book by the oil of their hands rather than the back of the book. And it turns out if you have any system whatsoever that's generated by the economy, it tends to follow this rule. And so what we did is that we created a vector out of that. We looked at the distributions at various aggregations for like banks or subnet or things like that, and then we just looked at how individuals would fall according to that vector where it should be, the Benford vector, and where a certain aggregation like subnet or the bank that they used or the city that they were filing from would be, and it would be kind of like out this way. So that's an inner product right there, which powers many of the algorithms that have already been previously talked about. And then all we would do is ask what's the angle between those two vectors. And that is this plot that you actually see on the screen right now. We did it for several amounts, so we have multiple dimensions of angles that we're checking against. And when we initially plotted this, all these points represent subnets, and so people aggregated by subnet, and then the Benford vector that that we observed from them, the distribution. And when we initially looked at all the angles and plotted this, these were all black points on this white screen and everything. And then what we did, we said, okay, let's apply the fraud flag. And blue represents the folks that the state of Indiana said was not fraud, and red represents the folks that were flagged as fraud. Just for a sense of scale, about the amount that exists, I think in the red, if my memory serves correctly, it's about $22 million. So that's quite a sum of money, and we found most of them just by looking at the first couple digits that they entered in a few of the numerical spots on their tax return. And if you think about it just for a second, I mean, think how scalable that is right away. As you bring in a tax return, you just start those aggregations. You start seeing how much people drift in their angle away from the expected Benford distribution. And as they kind of drift into the danger territory, you trigger an audit and then have returns. They might be fine. I mean, if someone's making 40K, it doesn't necessarily mean that they're fraud. But if everyone in that bank is making 40K, then maybe you should take a look. It's not always 100%. So we would go against like subnet, banks, several different aggregations, and we would flag people accordingly. This is a super fun thing because I mean, like I was saying earlier, this system took about 2 hours to actually run because we had to architect it in SQL for a whole bunch of reasons. I tried to make the algorithms move a lot faster than that typically, but and it basically did the work of 8 months of effort for the Department of Revenue for the state of Indiana, and it was quite an interesting result. And again, it's just by looking at those first few digits on numerical values on the tax return. We didn't have to apply any complicated methods. You could actually apply in this projection that we have of the angle space, something where you define a hyperplane between those two orbs and then you flag them. And that's fine. That's an example of this being a pre-processing step, and then you're separating out the rest of the orbs. But this on its own was a solution. And it was quite exciting when we found it. I remember having a party because we actually discovered this, and we could get away with not, using all these very, very complicated and black box methods. So another math hack that's very, very related to this, because we're talking about Cardwell law distribution here, is the hold on just one second, is the topic detection for NLP. So I was working at Demand Jump at the time, and we needed to Crap. Sorry, my computer's acting a little weird. Give me just 1 second. Silence these notifications. Sorry, guys. Like I said,
lost you a little bit.
Yeah, like I said, now I'll actually be able to focus. I'm sorry, guys. Can you guys see my screen now, or?
Yeah, it looks good.
Okay. Okay. Let me move this again. Sorry about that. So we needed, so back to this. We needed to do topic detection for natural language processing, and we needed a scalable algorithm, and we needed to be able to keyword things effectively for various marketing purposes and all that. So we wanted to link articles together according to like ideas. We wanted to be able to say the articles are talking to each other by X percentage, and then have some metric according to that. And a lot of the algorithms that we were seeing out there, and this was a few years ago, but so there's been some advancements since then. It seemed to be a post hoc analysis that we wanted to kind of avoid. We wanted to be able to take any article from any language and bring it in and be able to keyword it essentially. And these keywords had to be significant enough that we could build summarization later. We could build like little description text, all sorts of other things kind of to drive SEO, search engine optimization, for those who haven't worked marketing, and kind of drive our clients forward. So again, it came down to a math hack on the solution here. And this was, okay. I'm hoping that you guys can see this plot. I see my picture here, but it's okay. I can go around it. It came from information theory. So if you guys have ever taken a foreign language class, one of the things that you notice is that the shortest words in the language typically are the most frequent. We see this in English with the representing about 6% of the text that is written, and it goes on for a, and I, and so on. And the longer the word is, generally, the less frequent it is. And so if you're looking for things that the author is going out of their way to say, it is looking for things that don't follow this pattern in an article. So what we would do, we would bring in an article, we would read it, we would count the words, we would look at the probability distribution that we would expect from the length of the word and the compression that came out of information theory. And then we would just look for the words that didn't actually correspond to that. And those would be our keywords. Now, using those keywords, we then would say how much two articles were alike one another. We would, look at the intersection between the two, compare it to all the keywords that we saw, so the Jacquard similarity. And basically, if they met a certain threshold, we would link the articles. And the picture that's on the screen right now, that is actually an example of that, where we did this for the 2016 election. Each one of those circles represents different articles that were popping up at the time. And the lines between them represent a connection level, where we detected that a few articles were actually linked to one another. Now, you see a big glob that's at the bottom there. That represents the primary season. So articles are coming in, they're going on and blah, blah, blah about all these different topics. So they're kind of like, they're talking about the same thing, but it's kind of a mess, it's disjointed. What happens is that you see these tendrils that kind of go off, and those are different controversies that was very apparent during the 2016 election that evolved over time. And one of the larger globs towards the top of the image there is actually the Russia investigation. And we actually detected that during the election, that something was going on with Russia. We didn't know what it was at the time, or the level of interference or anything like that, but we could kind of detect something evolving. And using a very similar technique to this, if this method actually really detected what the intent of the author was. So if you were looking for things like fake news, the intent of the author didn't match someone who was actually trying to inform you on something. So all the fake news articles, at least the ones that we could find, and there might be certain situations where this doesn't necessarily apply, seem to be hanging out on their own, off to the side, and not really strongly connected, except for maybe one or two keywords just hitting for whatever reason. And so that was really, really cool. We could detect that they had the intent to deceive. And for demand jumps application, we weren't really in the political game or anything like that, but we were helping marketers figure out what they should talk about based off of this stuff. So if you have a company who has a large blog and they have their competitors who have a large blog, what we could do is link those articles together and say, well, your competitors aren't talking about this over here. Maybe you should write something about that. And here are some key terms that you might want to hit. And we could help them with the summarization or something like that. They have since advanced that since I've left, and they have some really cool stuff over there right now where they're working on all sorts of things of finding like relevant topics and all that. And they're using a lot of this early work as a basis for it. So those were two examples. I know I'm going pretty quickly, but I want to leave plenty of time open for questions. But so in general, when we're talking about math hacks, you generally can find these things by asking how the behavior would come about. So in the tax example, it's people making up numbers. People don't make up numbers the same way that the economy does or what have you. When people are writing an article, when they're talking about something that they care about, they tend to mention it. You could run into some pronoun problems where, certain nouns get substituted with he or her or what have you. But in general, you can detect what they care about by looking for the things that fall out of that, that fall out of the general pattern that you would expect from information theory. And if you can't tell, we're talking a lot about distributions. We're talking about inner products. We're talking about, probability and entropy and all that good stuff. We're using math to cut through a lot of the complicated stuff that you might, apply a random force to, or that you might try to push through an algorithm just out of the box and not really ever know what it's focusing on. And in general, if you find a hack and it looks like it's working, what's really fun about it is that in general, you can explain it to a general interested audience, not just mathematicians. So it's one of the strangest things in the world when you're sitting in a room and you're like, have you ever thought about this before? And it almost immediately it makes sense to everybody. It took a lot of work to get to that point, but it should seem so simple that everyone in the room thinks that they could have thought of that. And again, it's the beauty of a hack. It's like a heist that you go for, finding these really simple ideas that you can massively exploit to significantly shorten how much you have to write in code, all the assumptions you need to make, and make something that really scales very, very, very well. So those are some examples of that. So one of the big things that I wanted to talk about next is just kind of the toolkit that I use. So a lot of these are going to be very obvious to this audience. Actually, I'm pretty sure that this won't be surprising to anybody. NumPy, of course, TensorFlow, those are libraries for linear algebra. TensorFlow is very good at linear algebra. It's very, very fast. And once you can leverage those GPUs, it gets even better, which is amazing. A lot of times, visualization is key for finding these math hacks, finding the distributions, being able to call what a distribution is. Like, is it a log normal versus a normal distribution, what have you. And Matplotlib and a library called Seaborn is fantastic for that. You can start comparing two variables together. You can plot them out. You can see how it kind of falls out, and then run some experiments based off of the distributions that you observe and make sure that the behavior matches what you need. Network graphs or graph theory is a huge subject that's going to get more and more popular as time goes on. People are finding that if you arrange things like in a graph database like Neo4j or something of that nature, where you're looking at relationships between categorical variables, and you apply things that they initially worked on at Google, like PageRank and all that, you get extraordinarily significant results out that just kind of seem a little spooky, to be honest, but it's incredible. You start doing things where you start looking at the shape of these graphs, you start looking at the topology of this graph, and you find generating behavior. And this is picking up more steam in the AI community looking at things this way, looking for things like Betty numbers and all that. And NetworkX is a fantastic toolkit in order to actually start applying that stuff. Next thing is pandas. Again, I think everyone knows pandas here. It's the go-to library for manipulating data frames and all that. It's a fantastic system just to get something started up. You usually kind of drift away from it, at least in my experience, as you move on to production. But it's fantastic to just get something stood up right away, start applying analysis, adding aggregate calculations and all that. And then, of course, you have your go-to AI machine learning implementations like scikit-learn, SciPy, NLTK, and Spacey. Those are fantastic for standing up something quickly for AI. They also have a bunch of things like the hashing trick and various transformers for your data that does a lot of this math hacking for you right away so that you can start getting right to the math and looking at how things actually combine and all that. I tend to like to code my stuff from scratch using NumPy and TensorFlow just because that's me. But these are fantastic open source libraries that can really kickstart any sort of hacking that you're going to do or AI in general. So the next thing that there's two more things that I really want to talk about because I feel like a lot of times they're left out. So when you're looking for these things, there's no clear cookbook for math hacks or finding those hacks to be maximally effective and bypass a lot of the complication. So what I generally say is look for inspiration in places you don't expect. Podcasts like Radio Lab, 99% Invisible, and Numberphile are fantastic. The Benfords Law thing, the podcast that taught me about that was Radio Lab. And I find a lot of the design aesthetics of what 99% Invisible talks about directly applies to a lot of my work, especially when I'm talking about data architecture and that sort of thing. YouTube channels are huge. Numberphile, you have the best mathematicians in the world talking about all the techniques that they use, specifically how to think numerically and think mathematically about things, which is really, really cool. Computerphile is some of the best resources that it's one of the best resources that you can get quick snippets about how algorithms work and data structures and things like that are very important. Vsauce is, of course, extremely, Vsauce is a web video series that taught me about Zipf's law in particular. And it is a fantastic resource. To just kind of think about things in an oddball way and apply a new lens problem that you're working really, really hard on. They're the ones that first pointed out the commonality between all languages, and it allowed us to create an algorithm that works in all languages without any training whatsoever, which was really cool. And I wanted to specifically call out MIT's AI courseware that they have on YouTube. That's really good stuff, and if you do the coursework along with it, you'll have a fantastic footing for this field. In general, I'm a little bit skeptical of some of the online courses that exist, but I've gone through that, and I think back to when I was getting trained in school for this stuff, and it is absolutely fantastic. And I wanted to mention one book. I know it says books, but one book, and I actually have a copy of it right here. It's The Programmer's Introduction to Mathematics. This is all in Python, and it will give you the resources that you need in order to apply these math hacks. You'll do things like programming neural networks from scratch, which is really, really useful to actually know what's going on when you're working with a neural network. And it will talk about the fundamental mathematics that exist behind a lot of the concepts that drive things like data structures and projections and all that sort of stuff that is absolutely critical to data science and being successful in data science. The last thing that I really, really wanted to cover too is oftentimes people ask me what math should they be familiar with in order to do this data science in general, and also these kind of math hacks that I've shown a few examples of, and this is it. And I don't want to just give you guys a list and say, oh, here's all the math that you need to learn. I want to kind of go through and explain like where this stuff is used. So calculus is all about, it's a math of change. So if you're looking at a trend line, if you're looking at time series, if you're looking at gradient descent in a neural network, if you're looking at any kind of minimization problem, that's all calculus. And ideally, you should go through differential and integral calculus and also multivariable calculus. Linear algebra is probably the biggest thing on this list. Linear algebra is how most of these techniques work fundamentally. You're taking a vector, you're multiplying against a matrix, or you're going into more advanced stuff with tensors, and you're getting some result out, and you're doing some modification of it from there. Differential equations, you'll learn a lot of techniques on how to solve differential equations, like differential equations of motion and all that. But the best takeaway from differential equations, in my view, is the art of approximation. Most differential equations you can't solve explicitly, and you have to try and fit a function to them. And that is extremely important for a lot of things that you see in data science when you can't actually, come up with an explicit formula. So you end up doing like a Taylor series approximation or something of that matter. Real and complex analysis, that's all about how numbers work, both complex and real numbers. Graph theory, we already talked about. Probability and statistics is absolutely necessary for things like distributions, but also for Bayesian inferencing and general predictions and general predictions across the field. You can say some crazy things with Bayesian statistics, just looking at things like census data. And it is incredibly powerful stuff. Abstract algebra is huge just because you'll find, especially coming from a Python background, that a lot of the formalisms that you learn actually follow the rules of abstract algebra. So abstract algebra is a way to take programming languages in general and convert them directly into math, which is cool, so that you could look up theorems that might be solving a problem that you're working on and bypass, infinite loops or anything like that, and just hop and skip to the answer using something called group theory. And that is encapsulated within an abstract algebra. And the last one I put on here is, just because I've heard this a lot, is set theory, particularly because SQL is difficult. I hear that too often, that people, they come to SQL and it's so different from a typical programming language or framework that they've learned. And if you want to know how a mathematician looks at SQL, set theory is where it's at. Once you learn enough set theory, you'll actually be able to go from a set theory expression directly to a SQL statement. And it's really, really cool. You can start using that math in order to cut through a lot of the nonsense that you kind of run into as you're trying to do these super complicated queries against a database. And that's very useful when you're getting data in. And also sometimes you have to deliver through SQL, and that's very useful in that case as well. So that's the talk. I think I was a bit fast, but I am happy to answer any questions anyone have. If you want to talk individually, that's my email on there. And yeah, so I'll just open it up, Caleb. So.
Yeah, so if anybody has any questions, you can either post in the Slack or in the Q&A section of Zoom. There's nothing in either of those queues at the moment. But there is one comment, which is from Malcolm Newmeyer, which is in the Zoom chat thing. It says, Zach, the math subject slide and explanation was excellent. Great context, as most of us want to program and not solve math problems.
Yeah. No, that's fair. I see them one in the same, as strange as that sounds. I don't know, but I'm a math nerd first. I'll be honest about it. I use Python, but my degree was in physics and math, so that's in general how I approach it. But I do highly recommend going through like these subjects, even if you don't want to solve the math necessarily. Being familiar with this, probably you'll find it solves a lot of your the programming problems that you deal with just when you're building new products and all that good stuff. Any other questions or anything like that?
Nobody has posted anything, but I had one, which is like, as you like approach like your work, right? Are you just always like trolling for these math hacks, or like, do you like?
Okay. So if I was more professional, I would probably say, oh no, I only look for these when they're valid, but no, I'm always trolling for this stuff. I personally love finding something that bypasses like really complicated things, and it's kind of like, oh, I'll show you sort of thing. And there's a certain amount of joy that comes from saying, rather than applying this, why don't I just look at the first couple digits when solving a fraud problem?
Cool. So there's another question. Are there what are good introductory resources for these math topics? Specifically, I have junior developers to coach. Aside from that one book you mentioned, what?
Actually, that's a fantastic question. So this is where I lean really heavily on YouTube. So Numberphile is a big one. Numberphile that several of your students will probably be familiar with. Brady Heron does a fantastic job. And within the orbit of Numberphile, I'm forgetting the channel names. I watch your videos all the time, but I have a bad memory. What can I say? You'll find explanations of a lot of these things that focus heavily on visualization and not so much formulas. I mean, I'm a math guy, and I get lost in some of the paragraph-long theorems that we see. Everything becomes much easier when you can see a picture of it.
I can think of 3 blue, 1 brown.
Yes. His visualization is great. I didn't bring it up because I didn't want to say 2 blue, 1 brown. I couldn't remember what the numbers were or anything like that, So, like I said, bad memory, but his videos are fantastic, and he actually goes through calculus and linear algebra. And he does this introductory text with all these visualizations. It's really, really cool stuff.